moon, a celestial marvel in the night sky. It has captivated humanity for millennia, its soft glow illuminating our nights, its phases marking time's passage. But what if you discovered this familiar friend is slowly drifting away? It's true. The moon is, in fact, moving away from Earth. Don't worry, it's a very slow process happening over millions of years. This separation may seem like a detail from a science fiction novel, but it's a fascinating reality. Buckle up, as we're about to embark on a cosmic journey to understand this intriguing aspect of our universe. The moon's journey away from Earth is not a sudden sprint, but rather an elegant, drawn-out waltz. The moon is currently moving away from us at a rate of about 1.5 inches per year. That's roughly the same speed your fingernails grow. Over millions and billions of years, these tiny increments accumulate, significantly impacting the Earth-Moon system. By studying the moon's retreat, scientists can piece together clues about Earth's past rotation and the formation of the moon itself. To truly grasp the concept of the moon's retreat, we need to delve into the fascinating world of physics, specifically the realm of gravity and tides. The moon's gravitational pull isn't uniform across Earth's surface. This uneven pull creates bulges of water on opposite sides of our planet, leading to the phenomenon we know as tides. As Earth rotates, these bulges are carried slightly ahead of the moon's orbit due to our planet's relatively faster spin. This slight misalignment creates a gravitational tug-of-war between Earth and the moon. The Earth's rotation transfers some of its rotational energy to the moon's orbit. This energy transfer causes the moon to spiral outwards, slowly increasing its distance from Earth. The moon's gradual retreat is a testament to the dynamic and ever-evolving nature of our universe. Understanding this phenomenon provides us with more than just astronomical knowledge. It deepens our understanding of our planet's history and the interconnectedness of celestial bodies. We'll explore its connection to the concept of angular momentum, the phenomenon of tidal locking, and the implications for Earth's tides and future. Stay tuned as we continue our journey to unravel the mysteries of the moon's great lunar drift. We've established that the moon is moving away from us, but to truly comprehend this cosmic drift, we need to grasp the scale involved. The moon is currently distancing itself from Earth at approximately 1.5 inches per year. Picture a small coin like a dime. That's roughly the amount of space the moon conquers in its outward journey annually. Over millions of years, these tiny increments add up to significant changes. Since the extinction of the dinosaurs about 66 million years ago, the moon has drifted approximately 1,600 miles further away from Earth. That's roughly the distance between New York City and Los Angeles. You might wonder how we can possibly measure such a small distance with accuracy, especially when dealing with a celestial body hundreds of thousands of miles away. The answer lies in a remarkable feat of scientific ingenuity: lunar laser ranging. During the Apollo missions, astronauts placed special reflectors on the moon's surface. Scientists on Earth can now bounce lasers off these reflectors and precisely time how long it takes for the light to return. This technique provides incredibly precise measurements, allowing scientists to track the moon's movement with an accuracy of millimeters. Measuring the moon's distance isn't as straightforward as it may seem. The moon follows an elliptical orbit, meaning its distance from Earth constantly changes throughout its monthly journey. The Earth sits off-center within this ellipse, closer to one side than the other. This means the moon is closest to Earth at a point called perigee and farthest away at a point called apogee. When discussing the moon's drift, scientists refer to the average distance between Earth and the moon over time. This average distance, while constantly increasing due to the moon's retreat, helps account for the natural variations in the moon's elliptical orbit. So how far is the moon from Earth right now? Well, remember that due to its elliptical orbit, the answer constantly changes. At its closest, known as perigee, the moon is approximately 225,623 miles away. At its farthest, called apogee, it's about 252,088 miles away. These vast distances make the moon's 1.5-inch annual retreat seem even more minuscule. However, as we've learned, even small changes can have significant consequences over astronomical timescales. We often think of gravity as a force that simply pulls things down, like an apple falling from a tree. But gravity's influence extends far beyond our everyday experiences. It governs the motion of planets, stars, and even entire galaxies. And it plays a pivotal role in the moon's gradual retreat from Earth. The Earth and the moon, despite their vast distance, are locked in a gravitational dance, each exerting a pull on the other. This mutual attraction is what keeps the moon in orbit around our planet. However, this gravitational tug is not uniform across the Earth's surface. This difference in gravitational pull is the root cause of tides. Imagine Earth as a giant water balloon. The moon's gravity, pulling more strongly on one side, stretches this balloon, creating a bulge of water on the side facing the moon. Simultaneously, on the opposite side of Earth, inertia causes another bulge to form. These bulges are what we experience as high tides. As Earth rotates on its axis, different locations on our planet pass through these tidal bulges, resulting in the cyclical rise and fall of ocean levels. Earth's rotation is much faster than the moon's orbit. This means that the tidal bulges created by the moon's gravity are carried slightly ahead of the moon's position in its orbit. Those slightly off-center tidal bulges, tugged ahead by Earth's rotation, exert their own gravitational pull on the moon. This gravitational tug has two important consequences. First, it acts as a brake on Earth's rotation, ever so slightly slowing down our planet's spin over time. Second, this gravitational tug pulls the moon forward in its orbit, like a gentle nudge from behind. This added energy causes the moon to spiral outwards, gradually increasing its distance from Earth. Think of it like a child on a spinning carousel. A gentle push moves them further away from the center. This cosmic dance between Earth, the moon, and their gravitational interplay highlights a fundamental principle of physics: the conservation of angular momentum. Angular momentum, in simple terms, is a measure of an object's tendency to keep rotating or revolving. In the Earth-Moon system, the total angular momentum must remain constant. As Earth's rotation slows down due to the braking effect of the tidal bulges, some of its rotational energy is transferred to the moon's orbit. This energy transfer is what fuels the moon's gradual outward spiral. This process of energy transfer and lunar retreat has been happening for billions of years, ever since the moon's formation. In the cosmic ballet between Earth and the moon, gravity plays the role of choreographer, orchestrating a delicate dance of push and pull. This cosmic dance has another fascinating consequence: tidal locking. Imagine a pair of dancers, perfectly in sync, always facing each other as they glide across the dance floor. That's the essence of tidal locking, a celestial phenomenon where one celestial body always shows the same face to its gravitational partner as it orbits. In the case of the Earth-Moon system, we only ever see one side of the moon from Earth. This isn't a coincidence. It's the result of billions of years of tidal forces slowly synchronizing the moon's rotation with its orbital period. To understand how tidal locking works, let's revisit those tidal bulges created by the moon's gravity on Earth. These bulges, slightly misaligned with the moon's orbit due to Earth's faster rotation, exert a gravitational tug on the moon. Over billions of years, this constant tugging acted like a brake on the moon's spin, gradually slowing it down. Eventually, the moon's rotation slowed to the point where it matched its orbital period, the time it takes to complete one orbit around Earth. You might wonder how we know that tidal locking is a real phenomenon and not just a cosmic coincidence. The answer lies in the moon's own geological record. Scientists have studied the moon's surface in detail, analyzing its craters, mountains, and ancient lava flows. What they've discovered is that the far side of the moon, the side we never see, is significantly more heavily cratered than the near side. This difference in cratering density provides compelling evidence for tidal locking. Tidal locking is not a one-way street. Just as the moon's rotation has been affected by Earth's gravity, Earth's rotation is also slowly being affected by the moon's pull. This means that billions of years from now, Earth will eventually become tidally locked to the moon as well. When that happens, one side of Earth will permanently face the moon, while the other side will never see our celestial neighbor again. For now, we can continue to enjoy the familiar sight of the moon rising and setting in our skies. We've explored how the moon's gravity tugs on Earth's oceans, creating tides. But this gravitational dance has another subtle yet profound effect. It's slowing down Earth's rotation. The moon's gravitational pull on Earth's tidal bulges acts as a brake on our planet's spin. This braking effect is incredibly subtle, causing Earth's rotation to slow by a mere fraction of a second per century. Scientists estimate that Earth's day was originally much shorter, perhaps only 6 to 8 hours long, shortly after the moon's formation. Over eons, the moon's persistent tug has lengthened our day to its current 24 hours. As the moon continues its slow outward spiral, its braking effect on Earth's rotation will persist, albeit at an increasingly slower rate. This means that in the far future, billions of years from now, Earth's days will continue to lengthen. Imagine a world where sunsets stretch on for hours, casting long shadows across the landscape. That's the kind of future in store for Earth as its rotation slows. Eventually, our planet's rotation will synchronize with the moon's orbital period, resulting in a day that lasts as long as a lunar month, about 27.3 days in our current time. Of course, this is a scenario far beyond human timescales, but it highlights the profound and ongoing influence the moon exerts on our planet, shaping not only our tides but also the very length of our days. As Earth's rotation slows and its days lengthen, the moon's orbital period will also be affected. Remember that in the dance of gravity, every action has an equal and opposite reaction. As Earth loses rotational energy, that energy has to go somewhere. Some of it is transferred to the moon's orbit, causing it to spiral slightly further away from us. This interplay between Earth's slowing rotation and the moon's increasing distance is a delicate balancing act, governed by the law of conservation of angular momentum. The total angular momentum of the Earth-Moon system must remain constant, even as the individual components adjust their movements. This intricate dance of slowing rotations, expanding orbits, and energy transfer will continue for billions of years, ultimately leading to a state of equilibrium where Earth and the Moon become tidally locked to each other. Imagine looking up at the night sky, billions of years from now. The moon, much larger and farther away than it appears today, hangs motionless in the sky, always visible from one hemisphere of Earth, while the other hemisphere experiences an eternal moonless night. This is Earth and the Moon in a state of mutual tidal locking, a celestial embrace billions of years in the making. In this distant future, Earth's rotation will have slowed to match the Moon's orbital period, resulting in a day and a month of equal length. This state of mutual tidal locking represents a kind of celestial equilibrium, a stable endpoint for the long and intricate gravitational dance between Earth and the Moon. While this scenario lies in the distant future, it provides a fascinating glimpse into the ultimate fate of our planet and its faithful companion. The Moon's retreat affects Earth's rotation, lengthening our days. This cosmic shift also impacts Earth's tides. Tides are driven by the Moon's gravitational pull. As the Moon drifts away, its grip weakens, altering tidal patterns. Strong tides occur when the Sun, Earth, and Moon align. These are spring tides. When at right angles, weaker neap tides form. As the Moon recedes, tidal extremes lessen. This shift will reshape coastlines and impact marine ecosystems. The Moon's influence extends far beyond the oceans, touching the lives of countless organisms in subtle yet profound ways. Many marine species have evolved life cycles intricately tied to the rhythms of the tides. Consider the humble horseshoe crab, whose annual spawning rituals are synchronized with the highest tides of the year. Coastal ecosystems will face transformative changes as tidal zones migrate and shorelines adjust. Some species may struggle, while others will find new ecological niches, highlighting life's resilience. As we peer billions of years into the future, the Moon's fate becomes increasingly speculative, yet undeniably captivating. The Moon, no longer a bright beacon, will have shrunk to a fraction of its current size. Its gravitational influence will have dwindled to a whisper. Earth will experience a day equal in length to a lunar month. The Moon will eventually fade into a cosmic footnote, a testament to the ever-changing nature of the cosmos. As our exploration of the Moon concludes, we're left with a sense of awe at the intricate workings of our universe. The Moon, a familiar sight, is engaged in a slow dance with Earth, choreographed by gravity and time. The Moon's gradual retreat has profound effects on our planet. Its gravitational pull has sculpted Earth's tides and influenced the length of our days. From horseshoe crabs spawning to Earth's rotation, the Moon's influence is woven into our planet's fabric. Understanding this cosmic dance deepens our appreciation for the interconnectedness of celestial bodies. The Moon's story reminds us that even constant features of our universe change over time. The Moon's drift from Earth is not unique. Across the cosmos, celestial bodies engage in gravitational dances, governed by the same laws of physics. From exoplanets to binary stars, gravity shapes the cosmic landscape. Studying the Moon's retreat offers insights into other planetary systems. Understanding tidal forces and gravitational interactions helps unravel distant worlds' mysteries. The Moon's story reminds us that our understanding of the universe evolves with new discoveries. While we've learned a great deal about the Moon's retreat, this cosmic dance still holds many mysteries. Scientists are refining their measurements using sophisticated instruments to track the Moon's movement. Ongoing research includes studying the Moon's interior. Analyzing seismic waves reveals more about its composition and structure. Scientists are eager to explore the far side of the Moon. The far side holds a unique record of the early solar system. As we conclude our journey into the realm of the Moon's great lunar drift, we're left with a profound sense of our place in the grand scheme of the cosmos. The Moon, a celestial object seemingly frozen in time, is engaged in a slow, deliberate dance with Earth. a dance that has shaped our planet's past, present, and future in countless ways. This cosmic ballet, far from being a mere astronomical curiosity, is a testament to the interconnectedness of all things in the universe. The same forces that govern the moon's retreat also shape the evolution of stars, the formation of galaxies, and the very fabric of space-time itself. The moon story is a reminder that we are part of something much larger than ourselves, a cosmic tapestry woven together by gravity, time, and the endless dance of celestial objects. As we continue to explore the universe around us, we gain a deeper appreciation for the beauty, complexity, and wonder of the cosmos and our place within it.